For the rest of the lecture, I would like to introduce part of my studies um, for my PhD dissertation because it was about remote sensing's application in urbanized areas. It was about urban heat island. And I would like to start with how to address UHI with remotely sensed data. Of course, this part is not something I proposed in my dissertation. It's a principle. It's generally how people address UHI with remotely sensed data. So the most direct indicator of urban heat island is temperature, right? So usually in remote sensing, we use urban land surface temperature to address UHI, which means the temperature of the surface of a city or urbanized areas. It's not air temperature, okay? Air temperature is more complex. It cannot be directly and accurately retrieved from remotely sensed data because remote sensors, they only accept signals reflected by the surface of the area interested instead of the air, right? So this is a thematic map for land surface temperature of Milwaukee County in Wisconsin, where I lived. So here is the legend. It's a grayscale thematic map. Bright areas are representing areas with higher land surface temperature, or we simply call it LST. And the dark areas, they are for regions with lower LST. So this map is for July 9th of 2001. You can see here we have large bright areas here to the southeast of the county. That's Milwaukee City and Milwaukee metropolitan area. So it's natural and it's reasonable that urban areas have higher LST, right? And here is another thematic map, but this time it's not for land surface temperature, it's for abundance of impervious surface. And you can, if you compare these two maps, you can see that the bright areas, they are consistent in these two maps. On the left side, we have bright areas within Milwaukee City. On the right side, we still have bright areas, largest bright area surrounding Milwaukee downtown and Milwaukee City. And in this map on the right side, bright areas, they are for areas with higher abundance of impervious surface. So if you compare these two maps, it's naturally to think that, okay, maybe land surface temperature and percentage ISA or abundance of ISA, impervious surface, they are positively correlated, which means that the higher the abundance of impervious surface, the higher the land surface temperature. That is actually correct. This is the principle I mentioned before. When scholars, they are addressing UHI in urban areas, this is a direct way to address the existence, to prove the existence of UHI, because the higher the abundance of impervious surface, the higher the temperature. And in urbanized areas, we usually have higher percentage ISA. So this is assumption, and it is also the fact when we're talking about addressing UHI with remotely sensed data. So here is another proof of that. So we have two scatter plots. Okay. On the left side, we have impervious surface fraction or percentage ISA versus normalized LST. You can consider this as a normalized indicator of urban heat island because it's normalized land surface temperature, right? So you can say if we use a linear function to carry out the regression analysis of this scatter plot, you can see that this red straight line is the result. Obviously, impervious surface fraction and normalized RST, they're positively correlated, which means when one of them is increasing, another one is also increasing. They are along the same direction. On the right side, we have another indicator of UHI, which is vegetation fraction. So the correlation between vegetation fraction and RST is the opposite of the correlation between impervious surface fraction and RST. This time it is negative. So you can see here, again, this red straight line is a regression function is addressing the regression function between vegetation fraction and normalized RST is negative, which means that more vegetation brings less RST. It makes sense, right? Because if there is vegetation, there is always more evaporation, right? And evaporation usually makes air and surface cooler, right, which will decrease the impact of UHI. So positive correlation between RST and percentage ISA, and negative correlation between RST and percentage vegetation. Okay, so that's a fact. But the problem is that we have something called neighboring effect. Okay, it means that these two scatter plots, they are pixel based, which means that for each pixel, we find a dot. We use a dot to address a pixel in your image. And for that pixel, you can retrieve the land surface temperature of it. You can also retrieve the impervious surface fraction or vegetation fraction of it, right? And these two scatter plots, they are pixel based, which means that they do not consider something called neighboring effect, which means that land surface temperature of an area is not only decided by this area's thermal condition, but also affected by its surrounding environment. What does it mean? It means that pixel-based correlation between RST and other factors is kind of biased. It means that that pixel's temperature is not only affected by itself, but also by its surrounding environment. So here is an example. For example, we have a very typical asphalt road going through this whole area, which includes suburb, downtown, and the rural area. Okay, so we just assume that, say, this road is addressed by multiple pixels, right? And we assume that for all these pixels for this road, they all have the same percentage ISA. If we do not consider a neighboring effect, all these pixels, they should have the same land surface temperature, right? Because they have the same percentage ISA. That's the thought of pixel-based method. But the problem is that this road is going through the whole city, right? In suburb, this road is surrounded by grass, trees, and the building facets, water bodies. These land cover types, they are typical in suburb area. But in downtown, there is less trees, grass, and there is barely water body. So in downtown, maybe this road is surrounded by building facets, other roads, pavements, and limited vegetation, right? And this road again goes to suburb and to rural area, which contains even more vegetation such as forests, agricultural lands, and even larger water bodies. So I'm going to ask you, I mean, in the real world, do you think this asphalt road will will have the same land surface temperature from suburb to downtown to suburb to rural? I don't think so, because I would assume that in suburb area and in rural area, this road has lower RST than this road in downtown area because its surrounding environment changes from one section of the city to another. And like I said, if this road is surrounded by trees, evaporation from trees could cool the surrounding air, could cool surrounding surface to make this road cooler than it should be in downtown area. So what I'm trying to say here is that addressing the relationship between percentage ISA and the land surface temperature pixel by pixel is biased, and we should take into account neighboring effect to consider each pixel's surrounding environment to better and more accurately address the relationship between percentage ISA and land surface temperature. So how to do that? Here is some, some experiments I did in my dissertation. So you can see that we have three figures here. They're covering the same area still. Again, it's Milwaukee City. So here is the downtown, and on the right side, we have a black area, which is a water body, Lake Michigan, right? And you can see that these three images, they're from different years. The first one is from 2001, another one is from 2006, the third one is from 2010. So I painted high percentage ISA pixels with three colors, red, green, and blue. Okay, they are for those with high, medium, and low standardized or normalized land surface temperature. What does this mean? It means that no matter red, green, or blue pixels, they are all pixels with very high percentage ISA, equal or larger than 70%. These pixels, they are highly urbanized, but they're all highly urbanized. Given that fact, they have different temperature. Okay, red pixels, they have highest temperatures. Green pixels, they have median temperatures. Blue pixels, they have lowest temperatures among all these high percentage ISA pixels. You may say, I cannot see blue pixels. I'm going to show you. They are along the lake shore of Lake Michigan, right? For example, here, some blue pixels here, and even more blue pixels right here. If you zoom in a little bit, you can find them. So you can see obviously that for pixels with different colors, they have different spatial distribution, right? Green pixels, they are majority pixels, right? They are everywhere, but they are usually along rows. They're usually around rows, and they are widely distributed within the study area. On the other hand, you can see that red pixels. Let me erase these polygons I just made. Okay, erase them. Red pixels are not widely distributed, and they are clustered in business areas. For example, downtown of Milwaukee and some non-residential areas, usually a shopping mall or industrial area. These pixels, they have highest land surface temperatures. On the other hand, blue pixels, like I mentioned before, they can only be found along the lake shore, okay? Lake shore between Milwaukee City and Lake Michigan, on the right, to the right side of the image, right here, along the shore. So obviously there is something different in terms of different pixels environment. Okay, so I used something called average filter to take into account the neighboring effect. So my assumption is that green pixels, right, they have medium temperature. They are widely distributed within the city. They're usually along the road, which means that there should be some trees and grass, and they can be found in residential areas. They can also be found in business areas, but not widely surrounded by other, say, buildings and impervious surfaces. And another part of the assumption says that red pixels, they only exist in highly urbanized areas, which means these impervious surfaces, they are surrounded by even more other buildings and impervious surface pixels. So blue pixels, they are very special. They only exist along the lakeshore, which means that they are surrounded by a huge water body. They are the boundary between the city and the very huge Lake Michigan. So these blue pixels, they are highly urbanized, but they have the relatively lowest temperatures because they are surrounded by water. Okay, how to address the big assumption I just made, right? Different pixels with different colors, they have different temperatures because they are surrounded by different types of environment. So average filter is here to address that. So by creating a window with a specific size, for example, 3 by 3 pixels or 5 by 5 pixels, on the image, the average abundance of impervious surface, in other words, mean percentage ISA, within the window is calculated and assigned to the central pixel. And this new value is called recalculated percentage ISA. So if you review the image enhancement lecture I introduced before, you'll feel that this average filter is very familiar because it's not something very complex. It's something I introduced before. It's just a spatial convolution. Okay, I introduced in that lecture. So basically you open a small window, and when this window goes across the whole image, it goes pixel by pixel. All pixels value will be recalculated as the average value of all pixels included within this window. Okay, so I tried different windows with different sizes. So what does the size of this moving window mean? It means the environment you want to include into this calculation. If the window is only 3 by 3 pixels, it means that you only want to take into account surrounding 8 pixels into your calculation, which means only very close environment is addressed when I'm trying to address neighboring effect. If the window increases, the size of the window increases to 5 by 5, even 7 by 7, 9 by 9, 11 by 11, it means that for each pixel, it's the definition of its surrounding environment increased a lot, from 3 by 3 pixels to even 11 by 11 pixels. But it's not always a good thing to do that, because if the neighbor is defined as a very huge one, some pixels, they may not have impact on the central pixel, and you actually used a very huge window to include those pixels have no impact on the central pixel into your calculation. That will actually lead to a less accurate correlation between land surface temperature and percentage ISA. So here I have 3 scatter plots for you. They are for 3 days, from different years. Okay, so the left one is for the image from 2001, and the middle one is for the image from 2006, and the last one is for the image from 2010. For each scatter plot, okay, it's between window size and R square. So R square is an indicator of correlation between 2 variables. Obviously, here 2 variables are percentage ISA and LST. So window size is from 1 by 1 to 3 by 3 until 11 by 11. So if the window is 1 by 1, you actually did nothing, right? Because if there is only 1 pixel, the mean value of this 1 pixel is still itself. So you can see here, when you actually apply a 3 by 3 window to the image, the correlation between percentage ISA and LST increased a lot. For example, for the first image, originally the R square was only around 0.12, and after applying this average filter, it has been doubled. It's above 0.24. And this trend is the same for all three images. And if you increase to, if you continue to increase the size of the window at 5 by 5, when you are applying a window of 5 by 5 pixels to the image, you have the peak of R square for all three images, right? When the 5 by 5 pixel window was applied, the R square here is around 0.25. It's similar for the second one, it's similar for the third one. But like I said, sometimes it's not a good idea to continue to increase the size of the window. You can see that when you continue to increase, now the window is 7 by 7, 9 by 9, or even 11 by 11 pixels. You can see this R square decreases dramatically, very fast. So it means that, okay, neighboring effect is there. You can use this average filter method to address that neighboring effect. But you have to be very careful about the definition of neighboring, of neighbor. If the neighbor is properly defined, for example, a 3 by 3 pixel neighbor or 5 by 5 pixel neighbor, then you can better address the relationship between percentage ISA and LST. But if it is poorly defined, you are very ambitious. You say, okay, I'm going to assume that a 7 by 7 pixels, 7 by 7 pixel window should be the definition of the neighbor, or even 9 by 9 or 11 by 11 pixels. Then you can say that the R square, the relationship between percentage ISA and LST is actually going to be even worse. Okay, still it's better than the original image, the original relationship without any average filtering method. But you can say that when you continue to increase the size of the window, the R square is not going to increase continuously. It is going to drop. So my conclusion here, what I'm trying to say here is that the neighboring effect is actually right there, right? When you take into account of neighboring effect, you can better address the relationship between percentage ISA and LST. You can use this relationship to predict the land surface temperature, but do not overestimate. Do not say ambitiously define your neighbor. Okay, define neighbor to make this filter window very big. That is actually making things even worse than before. Okay, so this is I think the third video of the lecture, right? I'm going to use another video to finish this lecture, and I will see you later.